In this video, we take a look at comparison tests in section 5.4. So the idea behind the comparison tests is to determine the convergence or divergence of a series. What we want to do is we want to take a comparison series, okay? So in all of these examples, we're going to be using B sub n. B sub n is going to be equal to the comparison series. Okay, that's going to be the comparison series, and A sub n will be the original series, or whatever you want to call it, the series that we actually want to determine its convergence. Okay, so A sub n is the series, the original series, the series that we want to determine its convergence or divergence. B sub n is the comparison series. So if we just take a look at this right here, this says that B sub n has to be greater than or equal to A sub n, which is greater than or equal to 0. If that's true, then if B sub n converges, then A sub n converges. All right, so the easiest way to understand this, I believe, is to think of it graphically. So I'm going to draw a little graph. And so let's just say that this is B sub n, and it is converging, okay? It's getting smaller and smaller. It's converging towards 0. This is B sub n. Oops. B subscript n. And let's go to a different color. And so if B sub n is always greater than A sub n, that essentially means it's always above it. Right? It has to be greater than it, so it's above it. So A sub n will always be underneath it somewhere, okay? So it's always going to be underneath it. So if A sub n is always underneath, no matter what A sub n is doing in here, if it's always underneath B sub n, then as B sub n converges, then A sub n has to also converge. It's kind of like a version of the squeeze theorem, right? Because just remember that the purple line, A sub n, is always underneath. It's always underneath B sub n. And so as B sub n converges towards 0, A sub n has nowhere to go except to also converge. So that's why if B sub n is always greater than A sub n and B sub n converges, then A sub n must converge as well. All right, so let's just take a look at the first example of that, which is right here. And so the series that we're working with is this, 1 over n squared plus 3n plus 1. So one of the tricky parts of using the comparison test is finding an appropriate comparison series. The appropriate comparison series, B sub n, has to be something that we already know whether it converges or diverges. And so two types of series that are very useful for doing this are the P series that we learned in the last video and the geometric series. We can tell by looking at a P series or a geometric series if it converges or diverges without really doing much of any work. So because I noticed that this is a polynomial in the denominator, with highest power of n squared, I'm going to compare it to 1 over n squared. Okay, so 1 over n squared is my B sub n. A sub n is the original series. So what we need to show, first of all, is that 1 over n squared, we have to prove this up here. We have to show that B sub n is always greater than A sub n. So let me get rid of some of this over here so I can do that. So I didn't actually show what was going on right here. We've done this in other videos, but basically to show that 1 over n squared is always greater than or equal to 1 over this, and that should be n squared plus 3n plus 1, we can try cross-multiplying. So when we cross-multiply, we end up with n squared is less than or equal to n squared plus 3n plus 1. Well, that's clearly true, all right? Because we have the n squared on both sides, but over here we're adding stuff to it. So this side has to be greater than this side. We could take it one step further and subtract n squared from both sides, and we would have 0 is greater than equal to 3n plus 1, which is also clearly true. All right, so we have established the fact that 1 over n squared is greater than or equal to 1 over n squared plus 3n plus 1 for all values of n. All right. Then we also know that 1 over n squared is a converging p-series. Well, if we know that 1 over n squared is a converging p-series and it is always greater than the original series, then there's nothing to do. We simply conclude that it converges. Okay? Therefore, we conclude that our original series converges. Let's take a look at a second example. So in this one, we have, this is our original series that we want to determine its convergence or divergence. And so I take a look at the leading term. Sometimes you just need to take a look at the leading term in the denominator. It's 2 to the n. Well, that could be rewritten as the denominator, all that could be rewritten similar to a geometric. And so we can compare it to this geometric series, because 1 over 2 to the n could be 1 to the n over 2 to the n, and 1 to the n is just 1 over 2 to the n. So we're also really comparing it to that. But that doesn't look like a geometric. This looks like a geometric. And not only does it look like a geometric, but it is a converging geometric. So remember geometric series, the 1/2, r is equal to 1/2, that is our ratio. And if the ratio, the absolute value of the ratio, less than or equal to 1, it converges. All right, so this is a converging p-series. So if it's a converging p-series, we then need to show that it is always greater than the original series. In other words, it's always above. So to go back to my little graph that I made before, if this is my converging b sub n, then I need to show that that's always going to be above a sub n. No matter where a sub n is in here somewhere. It's always going to be above it. And so it's forcing a sub n to also converge. And so we can do that the same way that I showed you in the last example. I can do that up here. I had a little bit of space. So we can say, okay, well, 1 over 2 to the n plus 1 has to be less than or equal to 1 over 2 to the n, to rewrite it like that again, to rewrite it like this. Cross multiplying, I have 2 to the n is less than or equal to 2 to the n plus 1. Well, that is clearly true. All right, so we have all the pieces of the puzzle together. We're done, really. All we need to do is draw our conclusion. Because our comparison series is always greater than the original series, a sub n, and because our comparison series, b sub n, is converging, we conclude that our original series also converges. And finally, the last one will take us back to the second part of this definition. The second part of the definition down here says that if b sub n diverges, then a sub n diverges, but only if b sub n is always less than a sub n. So b sub n has to be less than a sub n now. If it is always less than or underneath a sub n, and b sub n diverges, then a sub n diverges. And graphically, here's what's going on with this. All right, so let's see where I have a little bit, I'm going to do that right here. So here's what's going on there. We have a graph. All right, and so here is my b sub n. B sub n is diverging. It's getting bigger and bigger and bigger and bigger and bigger. Okay, that's my b sub n. It's diverging. And so if it's diverging and it is always less than or underneath a sub n, that means if a sub n is up here somewhere, no matter where a sub n is, it's going to be also forced to diverge. There's no way that it can come down here and start to converge, because it has to be above b sub n always. And that's the key here, is you have to show that, you have to show that a sub n is always going to be above b sub n. In other words, a sub n has to be greater than b sub n. And so we do that. We can do that the same way that we did before. First of all, it's a little tricky with the comparison series. Some people say, why compare this to 1 over n? It actually, the harmonic is a good series to compare to the logarithmic function in a lot of cases. So just kind of keep that in your little bag of tricks. So we can show that this is true, that a sub n is going to be greater than b sub n, and we can do that the same way that we did before. So basically cross multiplying, you're showing that n is always going to be greater than the log of n, which is true. All right, so we know that a sub n is always greater than b sub n, and we also know that b sub n diverges. B sub n diverges, right? Because this is a diverging harmonic. And so all we have to do is make our conclusion. Therefore, 1 over the log of n also diverges. So for all of these problems, there's two things you need to do. You need to determine a comparison series. Determine what your comparison series is. So let me write that down. 1, determine a b sub n, your comparison series. Then you need to determine if it diverges or converges. Converges or diverges. And then the next thing you need to do is determine whether, b sub n is less than or equal to a sub n, or a sub n is less than or equal to b sub n. Now be careful. You might have a comparison series, okay? You might have a comparison series that converges. So as an example, if you have your comparison series b sub n, if b sub n is, let's say, 1 over n squared, there is a converging p series. That is a converging p series. But then you find out that b sub n is greater than a sub n. It doesn't work. This test doesn't work. Because if b sub n is converging, okay, again, it's converging, then you have to show that, oh, I'm sorry, I did that the wrong way. If b sub n is less than or equal to a sub n, it doesn't work. Okay? If b sub n is less than or equal to a sub n, it's not, this test isn't going to work. Because if b sub n is less than a sub n, that means a sub n is up above it somewhere. And so even though b sub n in green is converging, a sub n could be doing anything it wants to up here. It's free to kind of go wherever it wants. It has to be the other way around. If b sub n converges, then b sub n has to be above it. That way, a sub n is below it, then it's going to be forced by the squeeze theorem to converge. And the same thing happens if b sub n is a diverging series. Then you just have to make sure that the inequality is going in the correct direction. All right. So those are 3 examples on the comparison test. And a similar test to that is called the limit comparison test, which I will do in the next video.